Thanks again. Yeah, I appreciate that. And so I thought I'd start with, the obvious question: what do I mean by patterns and perspectives, and what does this have to do with the future of Orebody knowledge? So it's easiest to start with an example. So I'll start with this, and the title here is "Perspective Reveals 3D Patterns in this Orogenic Gold Deposit." This is the Red Lake Orogenic Gold Deposit in Canada. And this is 50 years worth of drilling and underground mining. This is a side-on sectional view. So here's the kind of Archean craton surface. And then we're looking down over 1,500 meters. And what I'm going to do is spin this around in a little bit of a video. And then the gold grades will highlight. And then we'll see how perspective is really important for understanding structural controls, in this case, on mineralization here. So here it's spinning around. And then what I'll do, that it turns on kind of an X-ray feature where you can see the high grades through the low grades. And I've used this data set for over 20 years. I still think it's one of the best ones to highlight the importance of perspective. So you can see when it spins around, there's some view of a shear zone, but it's only when you tilt it, and that's what it's doing now, that you can see that there's actually a shear zone here, and these plunging fold hinges in the hang wall and footwall. So it's a really clear example of why perspective is so important, right? If you just look north at the same data set, you might see a bit of a shear zone, but if you look west, you won't see anything. If you look in plan, you won't really see much, but it's only when you look down plunge, in this case, 60 degrees down towards the northwest, you really see the kind of resolution of several 100,000 drill hole intervals into one relatively simple structural control that would be quite common in orogenic gold systems. So again, it's a really good example of looking at tens of thousands, hundreds of thousands of drill hole samples with the right colors and really understanding what's controlling the continuity of gold mineralization in this case. And I'll have a few other examples later on in the presentation. So really, why are shapes and understanding of the continuity so important? Well, it's really all about shapes. And this is a quote by Harry Parker. He was a very well-known, globally known kind of geostats and resource evaluation consultant for many decades. He passed away a few years ago. I had the luck and really good fortune to work with him very early in my career in Nevada. And this is a quote from his keynote at the International Mine Geology Conference in Adelaide 10 years ago. And this is what his statement, and he always had very interesting and smart things to say, but I'll read it out. Increasingly, reconciliation issues are related to the lack of ore body knowledge in terms of the locations of the geometric limits of ore, the inadequate understanding of the irregularity of the contacts, and the ability of mining to follow them. I think it's a really clear statement about some of the challenges we're still facing 10 years later, but again, they've been part of the industry for a long time. And what I'll try to do in this talk is present some opportunities to look not only at old data, like that assay data, but also a lot of the new data that we're getting from new sensing and scanning technology that can really increase our ore body knowledge. So why do we need the better ore body knowledge? Well, here's an example of opportunities and risks that I've kind of paraphrased from 2023 annual reports, mostly from major mining companies. And I'll paraphrase these, but these are right out of annual reports from last year. And I'll put them both up. It's a bit wordy, but I do want to work through these because this really does highlight the importance of ore body knowledge. So in opportunities, lots of companies talked about a better understanding of their geology led to an ore blending strategy that would reduce variability, which would increase their processing efficiency. Or feed optimization was required to improve recoveries, for example. Or to get safe and stable operations, you really want no surprises. A lot of that has to do with having no surprises in the block model or geotech surprises or anything like that. So that's obviously ore body knowledge. Identifying new critical minerals. It's not only the primary elements of interest, like precious and base metals, for example, but there's lots of opportunities with better ore body knowledge and new scanning and sensing systems to identify new minerals that could be recovered in existing assets. And obviously there's an opportunity to reduce the footprint. That would be from crushing and grinding, which takes up a lot of energy. If we can predict those areas a lot better, then we can really deliver ESG targets. And for another example is testing new leaching methods to unlock resources. So those are the opportunities, and these are some of the risks down here. And these are, again, the asset impairments that are not uncommon, where these are surprises that the company did not want to encounter. So in one case, lower grade and harder ore impacted mining rates and throughput. So that was a reason why they couldn't deliver on the promises. There was an unanticipated fault in a high wall that required a significant change to the mine plan. More infill drilling required to improve confidence in the mine plan. Metallurgical test work confirms that ore changes with depth. Should be no surprise, but in this case it was. And another example, a weaker fourth quarter due to lower than anticipated grades. So again, I just wanted to focus on those because these are real impacts that cost money or can deliver more value for an operation. So the key themes of this talk, there's really just three. Like I said, it's all about perspective, and not only physical perspective, but kind of mental perspective of how we look at data. Initially, it'll be about finding these 3D patterns in old and new data and improving the ore body knowledge and collaborating with ore body customers. So those are the three broad themes of the talk. And just to give a little simple example of perspective, you can find examples of these kind of optical illusions everywhere. And here's an example of just something where it looks like these blue lines are converging when you look at it just in plan. But then if you tilt that image forward by, say, 70 degrees, you can see that those blue lines are actually parallel. Now, again, this is one of these simplified optical illusion tricks, but it is, I thought it's a good example of how sometimes you just need to change your view and use the different perspective to find out what's really going on, or to find out how your eyes are tricking you. And this is what I mean by new data from new technologies. We have digital core logging. This is an example of LIBS, or laser-induced breakdown spectroscopy, showing the mineral assemblages and the mineral abundances in this piece of core. And there's obviously other scanning systems like hyperspectral and XRF and XRT. And then, so that's an example of some of the new technology that is around now. And I'll show some examples of this. And then coiled tube drilling system. This is from Minex CRC and the DigCT company that is commercializing this. This is a system that has continuous drilling, but there are a lot of sensors at the bottom of this drill hole by the bit, which tell you a lot about the measure wall drilling information, whether it's penetration rate. And then there's also downhole tools associated with this that tell you all the petrophysical characteristics of the ore of the rocks you're going through, the cover rocks in this case, and the basement rocks. And then digital mapping from drones, right? This is an example of mapping the minerals and the mineral contacts in an open pit, and there are a lot of these drone systems around. So that's just an example of what I mean by new technologies. And again, I'll be focusing mainly on the drilling side of this in this presentation. So again, the main theme is the data storm is here. And I thought I'd use this example of a storm. I took this photo with my iPhone from in Northwest Queensland. And I was pretty amazed I captured it in that much detail. I probably took it, it was right about here. But again, it's highlighting that this data storm of new information from new technology is really here, and we should try to do something about it. So here's a simple comparison, and again, very simplified, but just looking at typical outputs from manual logging. These are drill holes beneath an open pit. And these are the typical lithology or even alteration codes that we get from manual logging. and quite often it's quite hard to interpret the continuity or the connection between these drill holes. But when you look at the digital data that includes things like mineralogy and texture and chemistry, you can get much more detail in these same drill holes. And that also poses a challenge for mapping. But it's an important distinction. And why do we want this sort of detail in the digital data? It's because when we open up the ore bodies, this is what they look like. And this is mineral domains draped over an open pit surface. And it should be no surprise in hydrothermal or hydrothermal magmatic systems, we see this sort of complexity. And so the detail that we're getting from all this new scanning technology gives us an opportunity to build models that more accurately reflect this, whether it's just in mineral domains or geometallurgical domains. So here's a couple of quotes, just looking again at patterns in science. I like this one, "Science is the art of finding patterns in reality." This is from a book about the hunt for the Higgs boson from several years ago. And it really does apply not only to particle physics, but especially to geology, because we are looking for patterns, 3D patterns in the Earth's crust. And then the other quote is, maybe you've heard this before, "Science advances one funeral at a time." I don't think we need to be that serious about offering our colleagues, but sometimes the paradigms do need to shift, and it takes a lot of effort to get to that stage. So patterns in geoscience, again, no surprise. This is what our pattern-seeking eyes and brains really focus on. When we have 100% exposure like this, it's not hard to see the patterns, whether they're sedimentary or structural or related to weathering or erosion. Our eyes make sense of these patterns. But when we can only drill them in a very few places, we need to think about mapping between those drill holes to make sense of these patterns and look for them. So here's another example, again, about perspective, and this is maybe more about the mental perspective of things. These were displays that were on the campus of the University of Western Australia several years ago. And if you walked up to these displays from the side, they didn't make a lot of sense until you looked in the right orientation. And in this case, you could see it was an image of Barry Marshall, who maybe took that quote about advancing science with funerals too literally, because he ingested the Heliobacter bacteria to prove that ulcers were caused by bacteria. Luckily, he survived and he won a Nobel Prize. So this is a good example, I think, of kind of the mental perspectives that's sometimes needed. So we'll go back to geology. And again, this is another example of how perspective can reveal these 3D patterns that help us understand the continuity of mineralization in an ore body. This is an iron ore deposit. This length of the open pit is probably 3 kilometers. And what I'm going to do again is show several thousand grade control assays from blast holes, turn on that X-ray feature so you can see the high-grade iron ore, and then we can see how that makes sense. So zooming in a bit again, several 100,000 blast hole samples over many benches. You can see the high-grade iron ore in red, but it's only when you turn and look in a certain orientation, you can see these broad open folds. And that's no surprise in a banded iron formation. It's what you'd expect. But in this case, what was interesting is that here's the folds in the pit, but this was in an operation where the geologists couldn't actually access the pit to do their mapping as often as they would like. So it was, they couldn't go out there and put their compasses on this or even map these folds out. So it was really important to look at the grade control data to understand what was in the benches above to try to predict the real controls on continuity in the other benches below. And this is an example of maximum intensity projection, or MIP, and it was described by Jun Cowan in this paper, X-ray plunge projection from the Alzheimer Guide to Good Practice in 2014. He has some very good examples of that that are worth checking out. So here's another example of patterns in a porphyry copper deposit in South America. Again, several 100,000 grade control samples from blast holes. And again, I'm going to turn on several benches worth of data. and then look at copper, moly, and arsenic from those, and we can see some continuity that wasn't necessarily well understood because, again, this is another operation where it was a real challenge for the geologists to get into the pit and do any mapping, not only because of autonomous equipment, but also because of weather and all kinds of operational constraints that meant geologists getting out in the pit and mapping didn't happen as often as we would have liked. So here's the video, again, now looking straight down, several 100,000 samples, now turning on that X-ray, and you can see this is a breccia at the core. That was copper. This is moly. I've tilted a bit. And now looking at arsenic, you can see these arsenic-rich brittle veins, and then back to the copper. So these are screenshots from that. And again, this is looking at about 200,000 grade control samples in this part of the pit. Again, you can see this, the very sharp boundaries of this breccia zone at the core of this magmatic system, hosting most of the high-grade copper. But then looking at the arsenic, you can see this vein-hosted arsenic in red. That's greater than 150 ppm. And you can see these nice steeply dipping conjugate vein systems that were not mapped. And the interesting thing with this example is that the geotech team really took this and really embraced this method of mapping. So here's from a published paper on looking at these arsenic trends. The previous slides just looked at this northern part of the pit. And what the geotech team then, once they saw these very clear northeast striking arsenic veins and steeply dipping veins, you can see this cross section here, they added about several 100,000 more blast hole samples. So this is over, I think it's close to 600,000 blast hole samples in this case. You can see the scale here. And they identified this whole array of northeast striking veins that they couldn't map. They could only map a few in the high walls because that was the only place where they could do any scanning. But in the ore and in the very busy center of operations in these open pits, they couldn't map out these veins. And this figure on the right shows the lines shown in black are what the geotech team had originally mapped out. And all the red lines here are the new structures that they mapped looking at all this grade control data. So it's a really good example of this sort of information, again, kind of legacy information from, probably over a decade's worth of mining, really adding value to this operation because it highlighted all these structures that had previously not been mapped. And again, this cross-section here, you can see is right through this, showing the very steep dip of these arsenic veins, arsenic-rich veins. And again, this is a paper you can look up. This is the Los Bronces copper mine in Chile. So that's really kind of the fun part. That was in the title, I guess, the opportunity to use old data and find new understanding by looking at just traditional grade control data. And I've done that for many, many dozens of deposits for a long time, both as a consultant and working for companies. And it was one of those things that I can almost guarantee anytime you looked at several years worth of grade control data in that way, you could uncover things that had not been mapped in detail in active operations. It's a very common thing to do, to look for controls on continuity of mineralization, whether they're structural controls or lithological controls on mineralization. So here's an example of the new information that we can look at. And I'll show some examples of this in the subsequent slides. We have things like measure wall drilling and petrophysics data that we can integrate with things like the BlastDog. This is an index tool that logs autonomously or semi-autonomously blast holes. We can look at texture from things like optical and acoustic televiewer data. This is an example from DataRock where you can just look at something obtained objectively like colors from RC chips right? And if these are all very objectively captured, we can learn a lot just by looking at color. This is a hyperspectral mineral map from CoreScan, highlighting the different mineral assemblages, whether they're clays or silicates. So really clear mineral mapping that is very hard to do reliably with the human eye. And then this is an example of how we might interpret some of that. This is multivariate geochemistry looking with data mosaic, which is a tool that CSIRO has developed. So this is the ability to look at multi-element geochemistry down a hole and define different intervals based on that chemistry with using wavelet tessellation. And the whole point is that you can use all these different data sets and again, look at the, hold on, sorry. Laser pointer has stopped working. You know, is to look at all this detailed information and then start mapping out the detail in 3D. And that's really one of the key messages here, is that one idea is to consider drill holes as long, skinny outcrops to map in 3D. This is a slide I stole from some oil and gas modeling, reservoir modeling webpage, but this is a case where that's what's happening here. They're using the 3D seismic and the few wells in an oil and gas reservoir to map out the continuity. But the idea is the same, that now we have so much more detailed information about whether it's petrophysics or texture or chemistry or mineralogy, that we really should start looking at mapping or interpreting drill holes as a mapping exercise, as a 3D mapping exercise. So, and when you think about, for example, the plunge, you know, in the orogenic gold deposit, or looking down the hinge of folds, it's just like a mapping exercise that you'd learn in your first mapping course. You're always taught to look along strike or down plunge to understand what the continuity of some feature is. And in this case, if it's controlling mineralization, that mapping is really important. And I think, you know, there's still a leap to go from logging and looking at drill holes individually, or maybe just on section, compared to actually modeling or interpreting them in 3D, mapping between them in 3D with many hundreds of drill holes. And that's where you can get real value. And I think that's a very important opportunity, particularly with the new Orebody knowledge we're getting. So here's another example, and this is from information from the BlastDog downhole tool that I showed in the previous slide. And this is a LiDAR scan of a high wall in a coal mine, open pit coal. Here's the coal seam here, and you can see all the sedimentary features, the cross bedding in the just in the LiDAR survey from this high wall. And then when we look at the information from BlastDog, which includes things like gamma and magsus conductivity, and it's integrated with measure wall drilling data from the blast hole drilling itself, we can see that these features really do capture a lot of the sedimentary texture that we see in the high wall. I'll just go back and forth. You can see how in these holes that are pre-splits along the high wall, you can see you really are starting to map out the stratigraphy in a lot of detail here. And then if you step back, that previous slide was just over here. Now we've got the entire bench, and you can be pretty confident that even in these widely spaced holes, you can map out the sedimentary features in that high wall. And now just imagine if you had blast holes with this sort of information captured off an entire bench, you'd be pretty confident that you'd be mapping out the stratigraphy across that bench in quite a bit of detail. And this is information that, again, is a coal mine, so maybe the geology of the coal seam isn't that challenging, but this is something that might be important for the drill and blast teams to understand how best to blast the hanging wall of the coal seam to protect the coal. And these cross beds and sedimentary features might be an important feature for them to understand. So again, this is for the customers of the ore body, and I'll talk a little bit about that later, is, you know, if you think of the geologists as kind of the custodians of the ore body, the customers of the ore body are the mine planners and the operators and the metallurgists downstream who actually need to use this new ore body knowledge. So here's another example. of new data from new technologies that improves ore body knowledge. These are benches from base metal open pit, and they're multi-bench heat maps. So this scale here, this length of the pit is about, of these blocks is about 600 meters. And we're looking at silicates here and heat maps, just showing the intensity of things like plagioclase, orthopyroxene, clinopyroxene, talc, and chlorite and serpentine. These are the clay minerals on the bottom. And these are things that would very much interest the customers of the ore body, because the silicates and the hardness of the rock on the bench and material on the bench would control things like fragmentation or crushing and grinding through the mill. And the clay would influence things like recoveries and flotation in the mill as well. So these identifying the mineral abundances and the kind of the heat map view is really important. And what's more important is when you combine this, that's what this is, same data set. And now we're looking at just ore types, and there's 8 different ore types here that the mill classified based on proportions of silicate minerals and clay minerals. And again, this is after the fact. So the metallurgists would look at material going through the mill, and they could identify 8 distinct behaviors of the ore, depending on the proportion of clay and silicate minerals. And these had different behaviors in terms of throughput and recovery in the mill. And what happened in this case is that these colors were then simply painted back on to the ore control samples. In this case, I should say the mineralogy that I showed in the previous slide, that was from FTIR, that's Fourier transform infrared analysis, and that gives you a very quick and cheap method of finding mineralogy in your samples compared to quantitative XRD, for example. But what was interesting is that we painted these 8 different ore types onto this bench, and there's continuity. You can actually see that ore type 8, for example, has some continuity across this bench. And ore type 4, which is the yellow, has this sort of continuity. They're not just random. So it's actually showing that there is some kind of geological control underpinning these metallurgical characteristics, which of course should be no surprise. That's what geometallurgy is all about. But the important thing is that this was defined really empirically. So we just looked at the mineral assemblages, and then, not related to any kind of preconceived ideas about ore formation or deposit genesis, just painted these ore types back onto the bench and can see that there was continuity. And this is absolutely the sort of information that mine planners and metallurgists would be looking for. So again, this is about the custodians, the geoscientists, collecting this new ore body knowledge and information and providing really good information for the customers to get the most value most efficiently from the mining operation. And this is another way to look at it, kind of a systems view about how ore body knowledge supports integration between the custodians here on the left, which is really the geoscientists who are involved in better data collection. And with all these sensor types, we're collecting safer and faster digital data. It's more reliable because it's objective, right? Whether it's from drones or probes or scanning. And really that's highlighting showing us a more realistic view of the ore body, what it really looks like, what we can expect it to look like when we start to mine it, because we're looking at the mineral domains. And this gives us a much better understanding, obviously, of ore body knowledge, but also predictions, for example, for mine to mill performance. And really it's about making better decisions at the kind of customer end, where you can integrate all the sensor-based data from the ore body with the sensor-based data that's coming from the equipment in the pit, shovels and trucks, for example, or in the mill and during processing, and what's very much collected in integrated remote operations center. So I like to think of it as the geology, the geoscience detail that we're collecting over here with ore body knowledge, with improved ore body knowledge, is really the front end of the information that can inform these integrated remote operations centers. So this is the last slide, and there's really just 3 key takeaways here. It's really, again, looking at patterns, looking for patterns in old and new data with perspective. Here's, again, that example of the orogenic gold deposit. You know, if you looked at it in plan or in section, you really couldn't see it until you looked at it down plunge and along strike of the shear zone, which was 60 degrees down towards the northwest in this example. And I think there's a lot to learn from these legacy data sets. You know, I think we could really learn a lot by digging out grade control data just from simple assays from the last 20 or 30 years of mining. It's all digital somewhere. It might be on tapes or floppies, God forbid. But I think it would be really interesting to do that because it would give us a very good understanding of what these ore bodies look like. But more importantly, the new data that we can collect when we scan or probe holes or scan the core is the improved ore body knowledge that I think will reveal new minerals and new elements and new mappable patterns. And that's what I'm trying to show here, is that it's really important to, again, think of those drill holes as long, skinny outcrops and think about mapping between them. Because if it is, you know, we're trying to understand mineral systems here. If it is a mineral system, there has to be some continuity between the mineralization. Of course, it depends on your drill hole spacing, but if we understand much more about the texture and the detail within individual drill holes, we might get a better understanding without so many drill holes, at least initially, about what some of the real controls on continuity are. And the third point is really about communication and collaboration, to do it as early as and as often as possible with the customers of that ore body knowledge. And you know, as geologists, we should always be thinking about who those customers are, particularly in mining and metallurgy and processing and environmental and geotech. There were some good examples of that, you know, and how we can present that information in a way that is easily digestible for the mine planners and metallurgists. So I'll just finish with one quote. This is from Stephen Hawking, and he said, he didn't use the word ore body knowledge, I put it in there, but he said, the greatest enemy of knowledge is not ignorance, it's the illusion of knowledge, right? So it's not what we don't know, it's what we think we know. And that's where I think the opportunity of looking at this new ore body knowledge from new sensing and scanning technologies, and also looking at old legacy data sets will prevent us from having this illusion of knowledge. So I'll leave it there. Thanks.